Now, yesterday we were looking at the definition of random variable. The simplest form of the definition which is being taught in the very first year for random variable x is defined as a function from omega to r, where omega, as we said yesterday, omega is sample space or universal set. We have defined a more sophisticated definition, namely some class of subsets of omega to R, which is called sigma algebra or sigma field. This is I would say another definition of a random variable. Okay. Now, after doing this, there is a possibility that every time this codomain need not be maybe subset of R. Need not be complete R, but some part of it R. Some people this call as range also, codomain range, or another name given to is the what you call this state space, of which we are going to generalize later on, okay, or range set, whatever it is called. So, now this instead of R, let us denote it by a set A or set B, say, which is subset of R, and that is acting as the range or what you call the codomain for the function x. Now, you can categorize this. B could be either countable or it could be uncountable. Now, in countable I cover both the things, countable as well as finite. Okay. And uncountable means the interval type of sets. Okay. Countable means something like this type of sets. This is called typically countable set. And sets of the type A to B, open A, close B, open A, open B, etc. These are uncountable set. What I mean by uncountable or countable in simple language is that set is said to be countable if there exists a one-to-one correspondence from set of natural numbers to the set, and that is what we call in reality counting 1, 2, 3, 4, 5, 6, 7, 8. That is what the countabilities mean, that there exists a function f which is one-to-one such that the domain is going to be B and codomain is set of natural number, and that is what is denoted in mathematics equivalent. Okay. Now, if there does not exist such a function from set B to set of natural number, then such a B is called as uncountable set. Effectively, practically the same thing. We cannot count the number of points or number of reals in interval. Whereas, now here you can start, this is number 1, this is number 2, number 3. The simplest function here is f of n is equal to n plus 1. That is the first term is 0, 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3. And this is known to be one-to-one function, and from this B to set of natural number, and therefore, this type of sets are countable sets. Similarly, here we know that between any two real numbers there are uncountably many real numbers, and that is why there is no function which exists which physically able to count 1, 2, 3, 4, 5 reals. Okay? And that is why these sets are referred to as uncountable set. Now, this nature help us to categorize the random variables. Now, if x is a random variable, with support or range or codomain and this is normally denoted by script x in generality. This is an example which we were talking about, which is subset of R. Now, if x is countable, then such a x is called as discrete random variable. Now, if x is uncountable, then such a x is called as continuous random variable. Now, there are some situations which are more naughty, in a sense that if you have x which is something like this 0, 1, 2, 3 up to certain point number a union, okay. So, it is decomposed into two parts, one where there is a countability, other one there is an uncountable set. So, this is, in other words, to some extent the support is countable and later on it becomes uncountable, and that is why this neither fits into this nor fits into this. Okay. Such a case, the x is called as mixture random variable. Now, later on we will see that even a continuous random variable can be expressed as mixture of three different continuous random variables because the distributional properties are different. We have not yet gone into the probability mass function and probability density functions and so on. That is why we are not going on to that level, but mixture can be on the basis of support as well on the basis of models. It can be of the either type, but what we are concentrating as far as the stochastic process theory is concerned, where the classification is done for the stochastic process on twofold ways, whether time parameter is discrete or continuous, as well as the support or state space is continuous or discrete. Whenever these things come, I will elaborate on this. At the moment, let us concentrate on this, that there is a scenario something like this happens. Okay. The point which I was making is something like this. Let me quickly this is also termed as mixture, but it is of a different type. So, for example, if I have a graph for certain random variable, this is say age with respect to immunity. Okay. Now, we talk about scenario something like this. Now, see, this looks to be a variation among immunity depends upon age, is this path, then it suddenly take increasing path, then it takes again stable path, starts dropping down and again comes down. What it means that the behavior with respect to immunity and age shows various pattern at various ranges. So, it is a mixture behavior. It is not showing a similar structure on different intervals of age. That is the meaning of the mixture over here as well. Up to certain range, it only takes isolated values, and in the remaining range, it is taking all possible values, right. And why these variables are coming into the picture? Because somewhere the system is behaving in a discretized manner. On the other hand, once it reaches a minimum level, it continue to remain in that level or increases, decreases continuously. There is absolutely no in between isolated point. You cannot differentiate. What is the meaning of continuous? Means you cannot differentiate. Okay? It is a very difficult question to ask. Why continuity or what continuity exactly means? Because when we teach in the first year of statistics course in BSc, we say that when you have a continuous random variable, probability x is equal to 0 is always 0. And student asks a question, look, I got a value of this. How can you say that it has a probability 0? Say for example, if you measure the width of a wire, you say that okay, this is the width of a wire which is taking okay 25.7 centimeter, 25.7 millimeter, whatever the units are. Now, what happens over there is you got a number and the student will say okay, I will get it this way. Now comes the question, if you measure next time, what will happen? Because of the measurement error, because of the capacity to locate the small thing, is what is going to happen is that the value is not exactly repeatable. What I mean by this is very simple example in physics. If you measure a small thin components using vernier calipers, your value would be different if you measure it with a screw gauge. So, what it means, at the most what I can say with great degree of confidence, that the value or thickness or the breadthness or circumference of this particular wire will be in this interval. I may not able to say exactly what value is for these quantities, and that is why this happens, the continuity. Okay. But in the some cases the wires are made in such a way that only the twisted parts break and then I say okay, this portion it is 1, this portion it is 2, this, and then I continuously and solder them together. Okay, little hypothetical situation, but what I wanted to stress is that there is a discretized jumps at some level and later on things become smooth. In a simple language we say that there are jerks or breaks, circuit breaks, like in common language which is used in the stock prices, the models with the breaks. What do you mean breaks? After this you jump here, you do not have anything between, but after a certain stage it is reached, it takes the value continuously between, then there will not be a much changes after that. That is what it is meaning something like this. Whatever the stability occurs is going to persist. There is not much variations which are going to come. That is what the meaning of the continuous behavior. Or if one trend is continued, that trend will continue later on. It will drop down, but there will not be any break. This structure, for example, will not happen something like this. Okay? There is no such breaks. But whereas, if you look at the another example, the simplest example, the number of wickets taken by a bowler in a test match. Okay. This will be x can take value in the set 0, 1, 2, 3, 4, 5, 6, and it will go up to obviously 20, extreme case. Both the innings, all the 10 wickets have been taken. We all know that the maximum number which has so far achieved is 19, not 20. Jim Laker had took 19 wickets against Australia, but maximum possible value is 20. Now here support or the state space or the range and codomain is not countable, but the sub part of the countable, and this is a finite support. But if I plot this on a graph, match number and number of wickets, now if I take the first match, it takes 0 wicket, this is somewhere here. If it next match it takes 4 wickets, it will go here. Match number 1 to 2, there is nothing. So in the match 2, he either takes this many or he will go from here to here. But you cannot have number of wickets taken as 1.5, 2.72. Between 2 and 3, there is nothing. 2 means 2. No matter the in between, if they are remain to be constant. As soon as you change from one match to another, it is going to jump. So if you more precisely, this graph will look like something like this. And why we are looking at match or here age? That is what is we are assuming. Match means the sample point. Now match number 1, let omega or this universal set will be the match number matches played, 0 match, second match, first match, second match, third match, fourth match. Now here the 1, 2, 3, 4 are even though numbers, they are not truly numbers, they are the tags. Match number 1 is omega 1, and in match number 1 a bowler takes 4 wicket, means the omega 1 is assigned the value 4 by this function x, and that is how it becomes random variable. This is very confusing sometimes. What people do, they think that it is 1, 2, 3, 4, how is it, now it is already number, why should I convert it? A simple example I can give to the students for elaborating on this. See, you have a name, you have printed on the mark list, but how do you tag in the classroom? You have been given something called PRN, permanent registration number. Now those looks to be number, but can you add PRNs? Can you multiply PRNs? No, that is what it happened. PRN likes omega i's. What will be x now? What will be x? Total GPA obtained by the student is my x. So what x does? It picks up a PRN and assign a GPA which the student obtained from a database. So what you get essentially, omega is, say for example, my PRN was 8721 or sorry 8727. And what if I wanted to have my MSc marks coming in x of 8127 coming out to say 55.95. So, this is my marks obtained in percentage. As soon as I say marks obtained in percentage or GPA on a 6-point scale, it becomes a continuous random variable. But if I wanted to recall how much marks I scored out of 22,000, 20 courses, 100 marks each, that becomes a discrete random variable. That is also an interesting part. How do you decide on the measurements? How accurate you want to measure? What scale you want to measure? That determines whether you are dealing with a continuous random variable or you are dealing with a discrete random variable. And in computer science language, what you call this as symbols or alphanumeric. They are not numerics because you cannot add them. If my another number, the student say 8128, my friend's number, I have to allot some marks to it. I cannot say that okay 8127 minus 1 will give me marks for 8128 or plus 1 will give me 8128, minus 1 will give me 8126. That does not happen. Okay? So, even though now what will be omega here is a collection of roll call numbers 8127, 8121, 8111 and so on. We have a class of 50 students. Okay? So, that's going to be the difference. So, even though you have these to be numbers coming in, similarly here age. Age is not to be added. What is interesting is the function which assigns some value to that age, namely immunity level, right, or maturity level, IQ level. This is my random variable because it changes from individual to individual. Even though the same age group person having different IQ levels. So, whenever you want to do some clinical studies, it is generally being recommended that your group on which you are working should be cohort. What do you mean by cohorts? They are homogeneous in the all characteristics in the context of the experiment. Like what it means by that is that if the immunity and other levels are homogeneous, then they will be divided into two groups, very classical efficacy studies which are very commonly being seen nowadays, medicine A, medicine B. One group will be given medicine A, the other group will be given medicine B, and the effects will be compared. Now, when you do that, if I already decided that the good immunity system people are to be given this part and the bad immunity people will be given the next. Obviously, even though the treatment is not good, because of the immunity, this shows that the treatment is good. Maybe both the treatments are equally comparable, they are equally effective, but because of the additional factor called immunity level which is higher in one group, it shows better result in that group. And that is why this is not a correct way of clinical trials. Similar thing happens in engineering. If I wanted to compare the two protocols of data transfer, X and Y, and I took the sample of data transmission for it, one protocol I will run on a workstation and other one is I am running on a desktop. This is not a correct thing to do, because configuration wise I have to have same configuration for the machines on which one uses one protocol, other uses the other protocol. In statistics we commonly do. If I want to deal with some modeling and I want to compute 25 by 25 matrix inverse, there are plenty of softwares and I want to compare which software is better. It is something similar to the two treatment which is more efficient. Okay. Now, efficiency has to be defined. At the moment we are dealing with a single random variable, so let us concentrate on the time required to get the answer. There are multiple things: memory usages, time required, accuracy, repeatability, and so many things. The simple example which anyone can try from computer's point of view, there are n number of activities in computers we do with simulation that is called virtual laboratories. Nowadays it is very common to use simulation. Okay, you go to any discipline of science or even management science or finance, and everywhere people do use method of simulations to verify certain results, verify certain protocols which are being designed. Now, within simulation, what is the very important factor is the random number generators, which are called pseudo random number generators. They are mathematical equations, but written in such a way that they provide you a sequence of numbers which almost behave like a random variable, sample from random sample, or the values of a random variable. Now, almost means what? What I mean by that, I have to write down what are the prerequisites or what are the requisites which I am looking at. Okay, for example, these are the requirement, and if these are satisfied with this amount of tolerance, I say that fine, this is a random number generator which gives me the kind of sample which I am looking at. Now, there as mathematics is progressing and progressing, people are coming up with a more and more different types of random number generators. It is not a very bad idea. In fact, it is a very simple assignment which we give in our first course in statistical computing in MSc to the first year student, that you collect all the random number generators, generate the sample of size 1000 from particular distribution, because they are students of statistics, and they perform various tests on it, test of randomness, test of goodness of fit, test of convergence, test about certain factors, certain estimators, and so on. And based on that, they wanted to see which estimator is good, and we classically give them the standard software which they use. You use any 4 or 5 softwares, collect the random number generators, generate the samples and compare them, and to tell you what result you get. Now, this is exactly similar what I was talking about in clinical trials. Now, here if I am using a software A on a workstation and the same type of activity with a software B on a desktop, naturally what is going to happen is that as I increase the volume of my data, the one will start deflecting down, other one will go up. Okay? And what I am going to get is one software, as far as time complexity is concerned, is bad or the worst or the not so good, whatever, the depending upon how much you get between the two. But now this is not a correct way to do it. These are not cohorts. You have to run the software, both of them, the competitive ones, on the same type of configuration. If that is the case, then you can compare. A similar thing happens over here, that whenever you are defining a random variable, you should know what you are actually measuring. Otherwise, this kinds of misunderstanding occurs, that my omega itself has the number, why should I map it? Because associated with every number, you have some score to it. Simple language in the gambling case, if you throw a die and there are numbers 1, 2, 3, 4, 5, 6, every number has a bet. Okay. Now, if I bet on 6 and if I invest ₹5 and if 6 occurs, will I get 10 rupees or will I get 7 rupees? Now, after doing that, if the die are thrown, if 6 occurs, that is success for me. But I am not going to get 6, but associated bet which I am going to win. If say 4 occurs, then I lost the bet. So, I have a minus score to my, it need not be always money, you compare the scores. And finally, cancelling plus and minus, you see what is the final gain of yours. You can try this one out. You can pick up 3 players, take the 2 numbers each for each one of them, throw the die and see how much pair comes and decide that if you win you get 1 this, if you lost this is going to be the gain. And now you see how much gain you get after you play 10 tosses, 20 tosses, 30 tosses. Just count it. Now to do this more systematically, that is need a modeling. And to do that modeling, we are to bringing in the what is the probability that these 2 numbers are going to occur if I throw the die. Now when it is unbiased die, we all know that any pairs either 1 occur or 2 occur will have probability 1 by 36, 1 by 6 into 1 by simple rule of chance. But that does not happen all the time. If the die is biased favoring certain number or die is biased against certain number, these probabilities kept on changing. Okay? So, yesterday I shown you that how to get the probabilities of x is equal to x. Now, let us concentrate first on a discrete random variable. Yesterday we have seen that is nothing but probability of event A, where A is corresponding event for x is equal to x. Now, suppose I want how do I calculate this? This is calculated as and what I will do is I will collect all these events A and corresponding probabilities and sum them. Or if I want to like this, now based on this activity of event chosen, every time going to the events and choose the event and compute probability will be time consuming. So, instead of that what we do, we try to find out can I represent this as a function of x and some theta, where this theta is called as a parameter. So, that will give me a formula if as I change the x, the value of this r, not x, r, I will get a different probabilities for x is equal to r. That is what my idea is. So, this is called as a very simple case of probabilistic modeling. Identifying the form for f x equal to r by making the way every time x is equal to r, then set of all points in omega for which x assigns value r. That collection will obviously the subset of the omega and hence defines an event. And you know how to compute the probability of events by 3 approaches. We are not going into that much detail because this much level I think everybody is familiar with how to compute the probability of an event. So, this is the first step of probabilistic modeling. Now, this law f r theta is generally referred to as probability mass function. what this now you cannot take any f for this, where the f has to be satisfy certain conditions. If I sum this for all values in support or range, or it should add up to 1, and probability of x is equal to r should be between 0 to 1 for every r. If this function is satisfying these two, it will be called as a probability mass function. So, in other words, what I need is f r comma theta r in x has to be 1, and f r comma theta lies between 0 to 1 for every r in x. This is called as a law. I will give you example later on how one can derive a simplest distribution which all of us know in probability, called binomial distribution. We will start with an experiment and a very general framework or a skeleton, and anything which experiment, any system satisfies this kind of framework, and you define a random variable or a mass or the function which can be used to numericalize the values, its distribution or probability mass function can be calculated using the law called binomial. I will come back to that little later, not now. Now, what we want to see, this is when the values are discrete. Now, let us talk about a continuous random variable. How does it happen in continuous case? This is for discrete random variable. Now, if I have x to be continuous, okay. Now, here what we have is not probability x is equal to x, but what we are interested in, the probability that x will lie between certain interval. Now, this I think this occurrence of continuous random variable is crystal clear if you concentrate on medical science. It is very simple. Why I am giving you again and again the medical science? Because everybody has someday or other come across these problems. Okay. We all undergo various pathological tests. Now, that does not say that if your HB content is equal to this, then only you are a healthy person. What they give is your HB content is between this range, then you are fine, you are not malnutrited. If your blood sugar is between this to this, you are normal, not diabetic. Okay. If blood sugar goes below this value, that means you are patient of hypoglycemia. What it means is the deficiency of sugar. If your cholesterol level is between this to this, then you are normal. So, everywhere now game is on the intervals. They are not interested in specific values, because this variability occurs among the individuals. You cannot pinpoint a single value which occurs in everybody, because how these standards are generally being done is you go collect the healthy individuals who do not have any complaint whatsoever of health and measure this. Now, you see a range of the people, and so as you do on more and more variety of people data, you realize that okay, this is a range if you have the people are healthy enough. Of course, it changes from gender, it changes from temporal in a sense that the American standards are need not be good correct for Asian standard. Asian standards needs to be little bit deflected in the Indian context or Russian context or Sri Lankan context and so on. Okay? Even though Russia has some part in Asia, some part in Europe, we cannot say that the convex combination of the two will be always going to be the fitting it. So, this is what slightly, so what meaning of the story is that you need to deal with this particular thing. Now, here you find fx comma theta which satisfies two conditions. Greater than or equal to 0 for every x in x. I will come back to what is the interpretation of this in a minute. Second, integral, in general people like minus infinity to infinity, because as I said in the beginning, the states support is a real line, but if it is not support of the real line, but its subset say a to b, this will be a to b, should be equal to 1, right. And what it means is the total mass is going to be 1, like what we had here. Then such a fx is called as probability density function. Because now what you have is it's extremely difficult to individually marked, right, and instead of that you will see how much dense things are. Now, as it happens in the earlier fr theta, which was probability that x takes value r, okay, but what will be this? Because as I said earlier, the single value is not possible and probability x is equal to x is 0, because you cannot be able to hit upon the exact value. So, what we do is in this context fx comma theta is nothing but probability of this is the meaning. It takes value in the very small neighborhood of length delta of small x, and that is called as this fx theta. It is not x is equal to x, please remember this, because this is where the trouble begins. Okay? So, what we are now dealing with a density function. Now, if I want to calculate probability of this type earlier, strictly speaking what I should get in the earlier way is that probability of x is equal to r running from x to infinity. But now there is very many numbers between r and r plus 1. How do I cover them? The simple way to do that is partition that r to r plus 1 as finer and finer and finer, and in that partition you compute the difference. That is what we do in Riemannian sum. And we say that as you make this interval finer and finer and finer, Riemannian sum will converge to something called Riemannian integral. Same logic will be used here, and this will be computed as x to infinity fx theta dx, and probability of x less than or equal to x is minus infinity to x dx. This is how now again f x theta is a model. You have to choose the model. Given the data, you have to choose the model which gives you this quantities probability of a range a to b. That's what the basic idea over there is. Okay? And so once this, now the real aspect of which we are trying to do now is identify this model given the data points. And what we are dealing in stochastic process is one step ahead. We are going to deal with the sequence of these creatures x1, x1, x2, xn. That is what I defined earlier. It is a sequence of random. I have not yet defined what is a sequence. We will see step by step. But at the moment now, we are dealing with random variable, that too real valued random variable. It is not vector valued yet and associated with this. Okay. Then if I define this particular quantity, it has a special meaning. This is denoted by f of x, and this is called as a distribution function of x. Obviously, when you have continuous random variable, it is computed like this. When you have a discrete random variable, you are computed like a sum. Whereas this quantity x quickly later greater than x will be 1 minus of f x, which is called as survival function of x. And this is the quantity which is normally the i's in the modulus. Next time what we are going to look at is a conditional probability, conditional expectation of random variable, and then I will talk about the vector value, how it is defined, and then we will see what is a sequence of random variable. That will complete our ground preliminary work to move to what is called the sequence of random variable and stochastic process, and subsequently we will go to the Markov chain. So, next job is to define what do you mean by a conditional probability, what do you mean by independence of two events, what do you mean by independent of two random variables. Before that we have to define what is a random vectors, and for how the vectors are different from the sequence, that we will separate it out, and then we will move to define the first dependent structure among the sequence of random variable called Markovian dependent, which we call Markov chains. Okay? Thank you.